Let's take a look at our homework from last night, right off the top here today, page 52, questions number 1 and 2. Any issues with either of those questions? I believe I saw when I checked these over that there were a couple people that had trouble with number 2. Is that right? Anybody for number 1? Number 2? Okay. Number 2 says, on-ramps are designed so that motorists can move seamlessly into highway traffic. If you guys have all driven at this point past the interchange at 22X, or what's now Stony Trail, and Highway 2 going north. It's only been open for a month or two, but it's a crazy interchange, right? There's like 12 bridges or whatever it is there. It's designed so that traffic doesn't have to slow down. Okay, and why is it designed so that traffic doesn't have to slow down? Because there's less chance of accident and less chance of traffic tie-ups there, right? That's on-ramps being designed so that motorists can move seamlessly onto highway traffic to the extreme. You can basically keep going at highway speed anywhere through that interchange and not slow down to 50 kilometers per hour as you're going through an exit. If a car needs to increase its speed from 50 to 100 kilometers per hour in a normal on-ramp, and the engine can provide a maximum acceleration of 3.8 meters per second squared, what's the minimum length of the on-ramp? I'm going to circle these kilometers per hour because we know that we don't want to be in kilometers per hour. When we were doing speed and velocity, kilometers per hour was okay. When we do acceleration, it's not okay. We need to be in meters per second. Let's write down some givens here now. Something is 50 kilometers per hour, which, of course, we're going to convert that to meters per second. But let's worry about what the quantity is first. Can you tell me what that is? It's velocity, right? But is it VI, VF? Is it V? Is it delta V? What is the 50 kilometers per hour thing there? At the beginning of this problem, the car is going 50. That's going to be V initial. Good, VI. VF will therefore be 100 kilometers per hour. We've got an acceleration here of 3.8 meters per second squared. Now, if it's speeding up, it's positive. If this car was slowing down from 100 to 50, maybe it was an off-ramp as opposed to an on-ramp, and you had to slow down from 100 to 50, then what would we have made the acceleration there? Not 3.8, but rather negative 3.8, because a negative acceleration means slowing down. And we want to find the minimum length of the runway. What are we looking for here? What variable is it that we're trying to solve for here? Somebody said it? I think I heard somebody say it. Yeah, it's the distance. Now, we're actually going to solve for displacement here, simply because we've got all the other vectors. But in the end, as long as we're not switching directions, distance and displacement will be the same number anyways, right? But you're right, technically. What's the length of the runway, or sorry, the on-ramp? It's distance. We don't need a direction with that. All right, what do you want to use? It's Group B problem, right? Because it doesn't involve constant velocity, it involves acceleration. It's a Group B problem. The equation that we want to use, I think, is going to be D is equal to VI. No, it isn't. You know what, let's go with that, though. I was going to say VI plus VF over 2 times T. Looking for delta D, so that's okay. Got VI, got VF, don't have T. Two unknowns. What do? You got a couple of options. You can either find T using some other equation, or you can just erase that equation and start again. Okay, I'm going to erase it and start again. Did I get the wrong answer here, by the way? I did not get the wrong answer. So if you pick the wrong equation, as long as it's a Group B equation, then that's okay, because the worst that's going to happen is what just happened to me. I had too many unknowns, wasn't going to work. Let's try another one. Let's try VF squared is equal to VI squared plus 2AD. I've got VF, I've got VI, I've got A, solving for D. That one's going to work, right? But I have to be able to rearrange this one. How many of you guys feel pretty good with rearranging equations? The algebra really is all it is, right? 2 of you feel really good at it? Wow. A few more hands go up now. We want to solve for D. Here's the rule. Get rid of what's not attached to the D first. Get rid of what's not attached. What's not attached to D? VI. What is attached to D? The 2 and the A. Get rid of what's not attached first. Now, how do I get rid of that VI squared? Okay? Subtract it. So it's going to be VF squared minus VI squared equals 2 times A times D. Now, we've gotten rid of everything that's not attached. Now we have to get rid of what is attached. So how do we get rid of the 2 and the A now? They're multiplied by D. I get rid of those 2 by... Awesome. Division, right. In the end, what am I doing here really is dividing both sides by 2A. The 2A cancels on the right side. So in effect, it's just dividing the left side by 2A. So VF squared minus VI squared over 2A equals delta D. Now, I've got a problem before I actually plug numbers in here. I've got to convert 50 and 100 kilometers per hour to meters per second. 50 kilometers per hour would be 50,000 meters over 3,600 seconds. And 100 kilometers per hour would be 100,000 meters divided by 3,600 seconds. This works out to be 27.7778. This one works out to be, what is that, 13.9, 13.85, 13.86, something like that? What does that work out to be? 13.8 repeating? Okay, so VF, we're going to make 27.777. Don't forget to square that. That's probably a pretty common mistake here. It's just saying 27 minus 13. It's 27 squared minus 13 squared. Divide that by 2 times the acceleration, and the acceleration is 3.8, positive because it's speeding up. That gives us delta D. Let's solve for that on our calculators now, just to make sure that we can all do that in the correct order. Let's say 27.7777 squared, subtract 13.88888 squared, get a number for that, divide it by 3.8, we should get 152. Wait a second. Oh, what have I done wrong? I got 152. Why did I get 152 when the answer is 76? Made a mistake here, not on purpose. I just made a silly mistake here. What did I do, Dustin? It's 2 times 3.8, not divided by 3.8. So it's divided by 7.6. When we do that, we should get 76 meters. Make sense? There is a tremendous amount of physics in highway design. Okay, we're going to learn later on in the year about curves and how you decide on the radius of a curve based on friction, how big friction is, and how you decide on what the angle of the curve on the highway should be. You know, when you go around a curve on a highway, sometimes they bank the curve. Okay, they do that because it helps you to stay on the road if there's ice, or helps you to go a little bit faster, okay, around a sharp turn. Okay. One of the most basic pieces of physics that we use on highways is those on-ramps and off-ramps, okay? You guys know if you've taken driver's ed, the whole point of the on-ramp is to speed up, okay? You're not supposed to slow down in a merge zone, right? A merge lane. You're supposed to speed up, and you're supposed to go onto the highway at highway speed, 100 kilometers, 110 kilometers per hour, right? How long does it take to do that? 76 meters. If you have a merge lane that's only 50 meters long, is it a good merge lane? No, because you're going to try to merge onto the highway at 80 kilometers per hour, and that's going to cause an accident because everybody else is going 100 or 110. So we want to make our merge lane at least 76 meters, probably even a little bit longer. Make sense? I'm sorry? Well, of course, it depends on the vehicle, right? It depends. Yeah, it depends on the vehicle. But a highway is designed for, not for, you know, the car that will go 0 to 100 in 4.2 seconds, right? It's designed for an average car as opposed to a high-performance sports car. You good? Okay, I want to do another example with you. This one is, unfortunately, one you're going to have to copy down because it's not in your book. But it's a good one. It says a 1,600 kilogram car begins at rest at a stop sign, then accelerates at 4 meters per second squared for 5 seconds. Then it travels at a constant speed for 34 seconds. Then it slows to a stop in 8 seconds. How far has the car traveled? There is nothing that we need to circle or underline here in red that tells us that we've got strange units or strange directions or anything like that. Nothing really like that that we need to draw attention to. But there are a few words. Well, there's one word that appears several times that's really important here. The word then. Okay, the word then. Every time we see the word then, something new happens. And every time we see the word then or something that means the same thing as the word then we've got to treat it as a separate problem effectively. So what have we got going on here? We got a car that's accelerating. Okay? When it's accelerating, we'll call that stage 1. Then we've got a car that's traveling at a constant velocity. Constant velocity for 34 seconds. We'll call that stage 2. Excuse me. And then it slows down. It's a deceleration. We'll call that stage 3. The mass of the car is 1,600 kilograms. We could write that down kind of before we write any of this stuff down because it goes with everything. Although in the end, we know that it's not going to matter what the mass of the car is anyways. It starts at rest in stage 1. When it begins to accelerate, it isn't moving. It accelerates at 4 meters per second. 4 meters per second squared, and it does that for 5 seconds. That's all we know about stage 1. It accelerates 5 seconds at 4 meters per second squared from rest. Now in stage 2, when it's traveling at a constant velocity, there's not very much at all we know about that, just that it travels at a constant velocity for 34 seconds. And then in stage 3, it slows down. It slows to a stop. So VF in stage 3 will be 8 seconds. The time here, VF will be 0 meters per second, I should say. And delta T will be 8.0 seconds. Do you see why it's so important here to write down my givens in stages here? Basically as separate problems. If we wrote it down all together, then we would make VI 0, we would make VF 0, and then we'd try to solve this problem with one single equation. It wouldn't work because as far as that equation is concerned, nothing would be happening. Right? VI is 0, VF is 0, nothing's happened. But if we look at it in steps, in stages, then clearly something has happened. It's sped up. It's gone at a constant velocity. It's slowed down. Now, if we want to find out how far the car has traveled, let's find delta D, the displacement, in each of these 3 stages. For the first one, let's say delta D is equal to VIT plus 1/2 AT squared. There's other equations, 4 other ones, in fact, that are valid, but this is the one I think is going to work the best here. VI is 0, so 0 times T is 0, plus 1/2 of 4 times 5 squared. That's going to give me 50 meters. So during that acceleration phase, it's traveled 50 meters. Do you see why we used a group B equation there in stage A? It was accelerating, right? Stage B, what are we going to do? I don't care about the answer right now. I just care about what are we going to do. What kind of a problem is stage B? It's traveling at a constant velocity. Is that a group A or a group B? It's group A. We haven't done one of those in a while, right? It's a V equals D over T problem. The only equation we have here to do this is V equals D over T. We'll rearrange that, take the T up by multiplying. Becomes V times T. But we don't know what V is. So we have to do something to get V. Any suggestions there? You guys are smart, right? You guys can figure this out. How are we going to get the speed of the object in stage 2? Yep. Good. Excellent. We don't know what the final velocity in stage 1 is, but we can find it. Now, at the end of stage 1, it's moving at a certain speed. That's going to be the speed that it moves in stage 2 with the whole time. So let's get in stage 1 VF. And we can do that. There's a couple of different ways we can do this. VF squared is equal to VI squared plus 2AD is one of them. VI is 0. VF becomes the square root of 2 times A times D. It's the square root of 2 times 4 times 50. 2 times 4 is 8, times 50 is 400. The square root of 400 is 20 meters per second. So at the end of stage 1, it's moving at 20 meters per second. For the whole of stage 2, it's moving at 20 meters per second. And the time here is 34 seconds. 20 times 34, is that going to be 680? 680 meters. Stage 3, what's happening? Is it a group A problem or is it a group B problem? Is it accelerating or is it traveling at a constant velocity? It's group B. It's slowing down, right? So we can use one of those equations from group B. Let's say, let's see here. Let's try D is equal to VI plus VF over 2 times T. Is that okay? VF is 0, T is 8. Oh, wait. Do we know what VI is for that stage? Do we? It would be 20, right? If it was 20 at the end of stage 2, then it was 20 at the beginning of stage 3. So we do know what VI is. It's 20 meters per second. VF is 0 over 2 times a time of 8.0 seconds. That's going to give me 20 divided by 2 is 10 times 8 is 80 meters. Let's add this to this to this. 50 plus 680 is 730, plus 80 is 810. The entire distance traveled here is 810 meters. Technically, it should be 2 digits because of this. 8.1 times 10 to the 2 meters. Is that a hard problem? Not crazy hard, but the thing is there's like 4 and 1, right? That's what makes it kind of tricky is it's not that any one of these things is hard, it's just that you've got to do 4 things. You've got to get the displacement in stage 1. You've got to get the final velocity of stage 1. You've got to get the displacement in 2 and 3. Add all those up. It's like 4 questions in 1. It's not crazy hard, it's just 4 times the work that a typical problem is. You guys feel okay about those? About that, I should say. All right, yesterday I gave you an opportunity for a short time to work on page 53, number 1 to 14. How far did people get with that? Didn't assign it for homework. Anybody get as far as number 5? Okay, how far did you get? Okay, perfect. So only one person got as far as number 5. We're going to give you a little bit of time to work on these questions here today, not the rest of the class, but some opportunity to work on them for class time today, and then there'll be homework for tomorrow. Okay, so get as much as you can done now, so you have less homework for tomorrow. Page 53, number 1 to 14.